Come on, you know, this is only four, Mike, come on up. I like the crowd being up here. Yeah, give them extra credit, it's just a discussion, I don't want to make it shout. Give them extra credit. Get extra credit if you move up front. Lance will give it to you.
They are,
Let me send you the exact URL. I'll give you a URL to the stream itself.
Pullman, I guess, was doing some background lab
Yes, but let me just send it to you. Let me send you the direct link so they don't have to do anything. So it's charles.bell@noaa.gov. Yeah, I can CC them as well.
It was the best thing ever. He left.
Neil.Baker.
I've never seen anyone so happy about it.
I talked to Kevin before, we have
When?
I drew up a diagram.
Yeah.
We focus on all sides.
Although we lost, but we still have to replacement.
That's what it's called.
Right.
Folks, usual rule for live streaming applies, and that's try to not use your Wi-Fi so we can conserve all the precious bandwidth that we've got, especially given some of the internet troubles the university has had.
Did Andrew tell you, did you see his message that he would be here till 4:30?
Yeah, that's fine.
Okay.
Okay, it's showtime. So, it's hard to believe that 40 years ago, you were going nuts, and I was in Boston watching the high clouds go by. And here we are. So I'd like to introduce Dr. Lucy Sahin, the Director of the National Weather Service, and also as the Assistant Administrator for NOAA, the Weather Services. I've known Louis, gosh, very long time. Yeah, 60s, yeah. You know, graduate school in there. And it's been very interesting to follow his career over the years. Prior to his current position in the National Weather Service, he was doing other NWS-related business today at the WFO, also checking out our building, the stats in the building. There's always issues with that. Prior to his current position, he served as the director of NCEP for 14 years. And he was responsible for directing the planning, the science, technology, and operations related to NCEP's 9 centers. I guess it's 10 centers now?
No, Water Center is independent.
Okay, I always get confused on it.
So do I.
In there. And prior to that, he also was speaking of new buildings, Louis was instrumental in getting the Weather Service a new building. And my former PhD student, Jeff Domego, who did excellent transition work for his PhD thesis, when he went to NCEP, or then NMC, they were talking about a new building. Jeff said, I'll be retired before they finish the new building. He almost made it
Yeah.
in there. So buildings always take longer than you can imagine. He was also the director of the office, NWS's Office of Meteorology from 1984 to 1994 to 1999. Chief of the Weather Service's National Meteorological Operations Center from 1989 to 1994. And section head of the Mesoscale Analysis and Modeling section at the Goddard Space Flight Center from 1978 to 1979, where he connected with Dick Kaiser. 89, what did I say? Oh, 79. 79 is on the brain. They store. He got all three of his degrees, bachelor's, master's, and PhD from the University of Wisconsin at Madison. And he's published more than 70 peer-reviewed papers, very, very active researcher. And he's really been a major contributor to the modernization of the National Weather Service and his leadership over the last decade. And what I especially like about what Louis does for the Weather Service is science drives the bus in there. Where we are at research, how to put it into operations, and so on. He's also the permanent U.S. representative of the World Meteorological Organization. I gather you are now a candidate for president of the WMO?
Yeah.
How do we stop the ballot? This is not recorded. I watch myself.
You're safe because the country gets one vote.
Country gets one vote.
Always country gets one vote.
Well, is there a Russian candidate?
And Louis has his executive officer with him today, Charles Bell there. I'd like to introduce Charles as well. Charles has been a meteorologist in the National Weather Service. He's done West Coast tours at Las Vegas, Anchorage, and Monterey, and he got his BS and master's degrees from the University of North Dakota. So I guess you're no stranger to cold.
Yeah, this is mild, spring day.
All right, so without further ado, Louis, let's bring up your presentation and get started. Working your eyes. We have slow computers. The speed of light is not quite as large. Can I? There we go. So let's go full screen. Let's see, what's the full screen option? Oh, there it is. Yeah. All right, so how do we get this to full screen?
Cancel. Lower right of the box.
Do enable editing
Yeah, you
too.
did the enable editing button.
Ah.
Close. Close.
It's so much easier on the Mac. Anyway. I'll get out of your way.
All right. So, thank you, Lance, for inviting me to be part of this class. Certainly, I'm looking forward to doing this. And hopefully, it's just not old war stories that we're here for. What I hope to do is at least provide an indication of this was not just a snowstorm that we enjoyed. At least I didn't enjoy it. It actually is more enjoyable knowing that he can get it. So it adds to the enjoyment factor. But this was a major, major storm that changed the whole research agenda for the country. And then really accelerated research operations in ways that we hadn't seen before. So what I want to provide is the issues, research challenges, the excitement of the research that we did, which I still think is relevant today. Maybe I've been so far out of the research community that I don't realize exactly all that's been done since but that's basically what I wanted to do. So, in 35 minutes, I have to do the storm. And then the forecast values that this time, I think the community is set up. You'll see the reasons why for that. To address not only the cyclone research, but also the forecast challenges. So this was really the first part of that we really had teeth to it. So after the storm, this rebirth of synoptic meteorology. Synoptic meteorology was dead. And if they're saying that to you today, ignore it. So We'll talk a little bit about that, the surge in mesoscale model development, and the opportunities and challenges. There are, I put things into I got references in Appendix A. We've made a difference. I got a short thing on the January 2016 blizzard, the Northeast blizzard, and you can see the advances we've made in forecasting there compared to what we had here. And then there's a telephone interview that I did the Friday after this. The storm happened on Monday. Chuck Wash recorded. I still have that. You can get a sense of how excited I get when you see it. Hibbard worked with me, and the visualization we did for this storm was the first application of this 5D. And I can tell you that the Space Science and Engineering Center was not enamored with this paper because he was working in a Unix environment. This was sort of proposed. And yet this was the first one. This is what launched his career, but when I presented this in Europe, the European Center offered me a job to come and work and make this work in their environment. I said, you're offering it to the wrong person who really want to give it. And that's what really got his career going. So anyway, let's get going. So here's a snapshot of the storm. 12Z, 19th February 1979. At this point, we were still getting about 4 inches an hour. Baltimore. Some places were getting 5 to 6 inches per hour of snow. You can see very clear illustration. People use this satellite image on television to illustrate it like a hurricane, but the asymmetric distribution of clouds here, low clouds to the south, the higher clouds coming into the north and wrapping around to the west. I was always emphasizing the asymmetric nature of the way we do asymmetric topic, the cyclogenesis is the key aspect of the surface. And you see, we were in the sweet spot in the mid-Atlantic region, anywhere from 23 to 27 inches of snow in DC, and it looks like Boston didn't get any, so that's his observations. His memory is still there.
I'll head even, but it's my turn.
Anyway, there are the maps for this, and I want to just note here on the 18th, this is one of the coldest high pressure systems we recorded. There were record highs in areas in Virginia and North Carolina that were lower than the record lows. That's how cold this area was, in the single digits. And you see this inverted trough in the first area of precipitation associated with that. That would be phase 1. And the difference between 0Z and 12Z is the rapid development phase of the storm, which is actually phase 2 of it. And that moved out, and it was a complete, and I think that you're going to talk about the pattern change that happened right after the storm. This was basically the end of winter. And then we had a 2-week period of snow and cold and all that stuff here, and then this happened, and it was over. You see I think the phase is a little bit better here. This band of clouds, much like what we're seeing today, with that band coming in and coming across. And that was the first area of heavy snow that hit from the Carolinas up into Virginia and Maryland. And then in panel C, you see this area developing now right over us. This is a 12-hour difference. I can tell you that between this, the weather forecast office actually saw this as the end of the storm and actually took down a heavy snow warning when that high cloud mass was exiting off the coast that you see in frame B. And then this developed overnight explosively and was not forecast or warned for. And that's what you can see now in the infrared here, you can see the asymmetric nature of the storm. So high clouds to the north of the center and low clouds that only picked up, and this is red to the south. So, 2 periods of cold, heavy snow warnings posted early morning of 18th of February. During the day, we got 4 to 7 inches in our area, more further south, associated with the developing coastal front. So that's phase 1. The snow stopped in Washington, D.C. area about 0Z on the 19th, so 7 o'clock. And it was at that time that the heavy snow warning was actually taken down before midnight. Okay. And then early morning of the 19th, by early morning, 18 to 20 inches of additional snow fell overnight in the DC area, 4 to 5 inches per hour. We had a few folks there in the map room of Goddard Space Flight Center that were very diligent about measuring, and they had 5 to 6 inches per hour measured in there, a little bit further south of where I was, for about 3 hours just before sunrise. I welcomed all the neighbors as they stepped outside. I was in the cul-de-sac cheering them on. It was an incredible sight. All right, so it motivated the community. The magnitude of the event. This was the second largest snowfall in Washington, D.C. history. The forcing debate. Okay, so there's a lot of this lower level versus upper level stuff. As I was doing my jet streak work, I had people actually influence what's going on the ground. This was at Wisconsin, and I tell them to look up. So you can see 300 millibars, right? Well, I guess so. And I said, but you can't see the Gulf of Mexico. And we know the Gulf of Mexico affects the weather just now. I was pretty mad, even as a, I couldn't help myself. All right, so diabatic versus adiabatic, and this is where Lance and I started going toe to toe in the debate. You know, especially me, I was sure this was not that pretty good. I was so sure of myself. And then the operational model failures, certainly we'll take a look at that. You should know, for those who get involved in the Cyclone Workshop, this was it, this started it. Ron Taylor, who was a program manager, contacted Don Johnson, my major professor, and then Peter Hobbs from the University of Washington, and they were principal investigators. And they envisioned maybe 3 or 4 workshops. I don't know, what number are you up to?
We're up to 19.
Yeah, so, but this is what started it. And you got the letter, you have a letter, you have a copy of that letter? Yeah. Okay, so phase 1 in the upper air. Now, I know this is going to come as a shock to you, but these are in isotopic levels. 332K, the pressure is on the right, so this is, you see the 200 millibar bullseye, let's see, right in, there's a pointer right there. Yeah, okay. Right in here, it's 200 millibars, so on this surface here, this is rising up, and you can see at 12Z on the 18th, and this was the time of phase 1, you see this 80 meter per second wind max, right near a ridge crest. So you got this general flow coming up here. In phase 2, when you look down in the lower levels, this is about 400 to 500 millibars. You start seeing this deepening trough here. And then 292, so this is 900 to about 700 millibars. You start seeing this flow cutting up the slope of the isotopic surfaces. In terms of upper level versus lower level, there's a ridge sitting over the coast. So the first inclination of those who were not, looking at just the old walls, like, how are we getting the snow onto the ridge along the East Coast? How is that happening? Right? So that was phase 1. So this is the 80 meter per second subtropical. We called it a subtropical jet. You can actually trace this back to this formation here. And then phase 2, now, instead of focusing on the upper levels, we start focusing more in the middle and lower levels to see how this trough, this is 12 hours later, this is the trough that's sitting upstream of the East Coast when the warnings were being taken down. All right, so we knew there was PV, but everybody was looking at the satellite, these clouds ripping off to the east, saying, well, this is not going to work, thermal field is, I don't know what. Okay, we didn't have access to the maps like you have now, right? So all of a sudden, the warnings get taken down with this trough in here. And you see at 292, a nice thermal ridge. If you look at these pressure fields, this would be a thermal field on, let's say, 850 millibar now. So there's this nice thermal ridge building up in here, very tight low. And you can see trough at the 292. So it's clear that within this area here, now in the lower and mid levels, you got an amplification. So the forcing debate, how could you get that upper level forces under a ridge? So what we did here, this is out of the first paper we wrote from McDonald, is this 332 surface. And here's the total wind. So you can see this wind field coming across. And at this time, it amplifies to 80 meters per second. And we derived this analysis by the cross-check program that Rob Peterson had, the pressure analysis, isotopic analysis, and cross-sections. So and we did a lot of this stuff by hand before we used these automated, valve automated systems. So we're pretty clear about what was happening here. If you look at the geostrophic wind, which is this panel here, you see a couple of things. First of all, the wavelength is decreasing between this trough and this ridge axis, but the geostrophic maximum is located right in here. And keep in mind now, the exit region of this geostrophic max is in the entrance wind. So if you're doing purely quasi-geostrophic, you're going to get a two-vector distribution. You're going to get an ageostrophic distribution that's actually different in sign between the total wind and the geostrophic. If you look at the ageostrophic wind, you get this nice, flow into the entrance region. Let's take this time here. Flow into the entrance region, perfect. Flow out of the exit region, looks pretty good. Then all of a sudden, you get with this shifting wavelength, here's your entrance region, and what you see is any pulse coming across here now is going to go through a second acceleration as this flow field is directed to the left of the G potential, okay? And it's this area here now with 30 meters per second ageostrophic wind, in which when we're computing the divergence, it's also increasing with time. So there's your forcing agent in the upper levels for this phase of the storm. And when we do our cross sections, get a nice indirect circulation. Turns out there was a low-level jet that formed in the lower branch of this circulation, approaching 30 to 35 meters per second. At this time, using just the analysis, we believe that low-level jet developed over a 12-hour period. Okay? But here's your vertical motion field. This is all derived from that analysis. So to set the context of this, we were looking at this from a deep tropospheric perspective, dynamically driven. And at this point in the analysis, this is it. Right? Just focus on this. This is it. And Lance was focused on this. What the hell's going on down here that gives you 30 meters per second wind, and how is the diabatics playing a role in here? And one of the things that Lance focused on, and Bob Atlas, who shared an office with me, so I had these arguments not only with Lance, I was having this argument in my office meeting all the time. And is that they were looking at sensible heating actually before the storm formed, which was opposite of what people were looking at sensible heat relationships to cyclogenesis either during or after. So this was new. Okay. So anyway, the low-level forcing involved with this, and I was looking at the upper-level forcing with respect to that. So the anticyclonic subtropical jet, coupled low-level jet with an indirect circulation of the coastal front provided divergent low level moisture flux for the heavy snow. End of story. All right, so then in phase two, we'll get to the model stuff in a minute, was what's going on in the mid-levels with respect to this amplifying trough. So the polar front digging trough approaches the east coast, the coastal front approaches poles. You'll see it's prior to and upstream of rapid site. This was also new, because everything that I read anyway, and Toby Carlson's book was one of the prime examples, was that tropopause folding occurred with cyclogenesis. So we're finding, as you'll see, a tropopause fold occurring prior to that rapid development phase. And then the heavy snow, of course, occurred with this on approaching the coast. And there's your fold. Here's that 12Z on the 18th. We took this right about in this part of the Midwest, and you can see the 10 line, the 20 line, the potential vorticity working its way down the front. And by 0Z, which is upstream of the East Coast in the Ohio Valley, you have this 10 line all the way down to 700 millibars. Okay, clear. And then to sort of reinforce this application, the first application of the TOMS ozone distribution, Arlen Kruger shared an office. Actually, I think he was in another building, but he was the TOMS program manager. And we found that you could use the ozone, which is in a sense, a surrogate measure for the depth of the stratosphere, was actually coinciding with this trope fold. And this was the first application of TOMS to a synoptic or even a mesoscale feature. The other first application, this is Dan. Dan was, joined us at Goddard Space Flight Center. I was very fortunate to be able to, I don't know if I talked you into it or you got tired of me trying to talk you into it, but he joined us.
You had maps on the wall.
Yeah, we had maps on the wall.
Nobody else was
And-
parking.
Yeah, and Paul and Keith Brill were there, Paul Coates and Keith Brill. But Dan joined us, and of course, he was working with Mel Shapiro and then on his own, on the two-dimensional structure of the forcing for frontogenesis. And what we did was, here's the sort of Eliason equation that Dan was working on, and then here's the objective analysis. You know, again, the sinking air, this was within the area of the tropical fold. I believe this is the first application of real data, right? When we did this, your story of Eliason.
Yeah,
What?
first.
Yeah.
Eliason had a graduate student do some examples with real data that they weren't published in refereed literature, they're in the grade literature. That's the only other one I remember.
Okay, so we were involved in this. Why is this important? Well, there was a view, and Norm Phillips, you know, one of the first meetings we had at the cycle meeting we had was at NMC, and Norm Phillips was sitting there. And Mel was emphasizing the importance of this, and it was, Norm just sits there very quietly and then asks a question like this, why should we care about this? After all, we simulate cyclogenesis with two-layer models. And, I said, sitting in the way back, and Mel, when Mel gets asked a question like that from people like Norm, he kind of hesitates a bit, and I couldn't help myself. I said, well, yeah, but it took you 60 hours to get a cycle, and it happened in 12 hours here, So, the point is, it turns out, here is that mesoscale processes actually had an influence on the synoptic scale circulation regime that exploded in a 12-hour period. And this is one illustration of it. The diabatic processes that destabilize, decrease the static stability immediately along the coast gives you a faster response time. And there's another mesoscale process. Okay, so one of the things that came out of here is that this cyclogenesis and these snow events can be mesoscale in nature. So, why did the model fail? Well, the LFM, which was the model, the key model, really the first model that actually showed precipitation field. As a student, we used to hang over the fax machine to make sure that the wire was in place and the paper was moist, because you never wanted to miss this model run, right?
Same thing happened here.
7 levels, right? Look at this PE was no limited area. This is more of a hemispheric. 127 kilometer resolution, 7 levels. Primary data source, radar data, and surface data. No significant level data issues. So you want to do boundary layer forcing in your model runs? You didn't have it here. Okay. Research community reaction, enough is enough, Cyclone Workshop, Energize, was because now, even by 79, the research community were doing mesoscale models in the research mode, whereas for the 20 years before that, they didn't have the computing resources to do it, so most, if not all the models were done in the federal laboratories. So this, as you'll see, turned out to be a problem. And you can see these are 36, 24, 12-hour forecasts for 12Z and 19th, and you can see 36 hours in advance. You just get this inverted trough. This verifies at the time that the low is already spun up. Got some indication of the low here, okay, with an inverted trough, 12 hours before. And this, I think this model actually came out after they took the warming down. So one of the things that I did or wanted to do was to see, in the research mode, whether we could simulate the storm at all. So the full physics run, we were able to we didn't get the full deepness of this storm, but we certainly got ourselves, a rapidly developing system at 12Z. So then what we did was we did fully adiabatic. And this was my first wake-up call, right? So it looked a lot like the LFM. The other thing is that we did the late heating, but no boundary layer. And you got a weak storm, But you actually got a stronger storm, the boundary layer, no latent heat. So this started telling me right off, once I got to, now this is like 5 years into the war, back and forth. This wasn't like, hey, we woke up right after the storm and decided to do this, right? So again, this was another wake-up call for me. You know, if you don't learn from your own research, you know, you're probably in the wrong business. So this was a clue that this boundary layer heating was going to be an important aspect. So with respect to the low-level jet, we did trajectories off the model output, 15-minute output. It took days to create these tapes, and then to extract the trajectories that we could actually show us. So adiabatic, we went from 15, 17 versus full physics, where we went 19, 21, 21, 31 meters per second. So, and the pressure is 921, 880, 850. So the adjustment is occurring over a 2 to 4 hour period, not 12 hours now, as the parcel is being lifted. And it turns out that the change in the pressure gradient force in the vertical now put the parcel perpendicular to height. That's when you got the acceleration. So this is a representation of the three-dimensional adjustment, whereas when we did the jet stream work and the inertial oscillations and things like that, you're looking strictly at 2D. And I thought I had just discovered the third dimension of the adjustment process. I called up my major Professor Don Johnson, they get all excited. He goes, I think you ought to read Newton 1954. And Newton actually summarized this whole process based on analysis, no models, detailed analysis of 2 cases. And he described it so perfectly, I wound up quoting him and attributing this again in the paper that we wrote. It was really beautifully done. So, we know that there's something going on here that's allowing this vertical lift that is creating an adjustment that's compressing the time from an inertial oscillation to a few hours, really tomorrow. And you can see this in the 900, 1000, 1100, 1200, how the ageostrophic wind just explodes right across the coast, and then the total wind field accelerates slightly inland. That's the creation of the low-level jet in a matter of hours. Now, the thing that Lance insisted that I should know, no, he didn't. He didn't see this. Full physics in the early phases, it's kind of interesting that we see, I was 3 hours on these charts, but the principal signal here for that first phase is that you get divergence aloft, but you also get this divergence along the coast where the entrance region of the low-level jet. So you see this mass divergence here? And it turns out that the boundary layer, no latent heating, is the only one that sustains that low-level signal. So this is where I'm basically ready to call Lance up and say, you're right. And it turns out we met in the middle, because there is, as you see when we get to phase 2, when we get back, this is Whitaker, Jeff Whitaker just came in as a student, worked with me, and then, and Tim did so much work with this. He was the first author on this paper. And we did back trajectories as part of, first of all, the conveyor belts seem to manifest themselves with these back trajectories. But what was interesting, we could follow the same box and do the divergence profiles. And look what happens. This is the first phase. Again, you see this double. And then overnight, you start going into the classic 2-level pattern. But what was an eye-opener for me is how low the level of non-divergence is, because we were told to always deal with the level of non-divergence at 500 millibars. Right? So clearly, this transformation in the rapid development phase to the classic 2-level pattern is there, and it didn't take long. And when you do the Viz 5D look at it, and again in the appendix, you get a chance. It's the actual movie we made. It took days to make that movie that you do now on the phone. But 0Z, you see this is the 2 surface, the PV surface, hanging down. As you look at it in the movie, it looks like a white tornado. And these parcels are moving with it, basically, more adiabatic. And then you see this second maximum goal right here along the coast. And these red trajectories actually pass on through and then out into the diabatic processes that are working there. McIntyre actually visited me in our office while we were doing this, and his eyes thought I was dead because he was working on the paper with Hoskins about this, finding the two structures. And one of the things you see, we have in the movie, you can see that there's a nice slope to this with time, and then as the low occludes, it goes vertical. So, you know, it's all consistent. All right, so the results: unbalanced flow. The quasi-geostrophic restoration of geostrophic and hydrostatic balance is not at play during phase one. It's going out of balance. You know, it's not going into balance with that flow going through the ridge. It's an unbalanced flow. Within 3 hours, related to the unbalanced subtropical. We actually computed the moisture flux with heavy snow, comparable to what you see in severe weather situations in the spring. Again, I give Newton credit here. There's it. The tropopause fold preceded and contributed. This is the old version of the slides, by the way. But on the new version, I got Bob and Lance's work. Really, they not only focused on evaluative forcing, they brought a different dimension to it with respect to the initial and the rapid development phase. The rebirth of synoptic meteorology, I had to put this in here with Dan sitting in the audience. We were doing a number of studies where we were using the models to actually do the diagnostic work and to unravel the evolution of the atmosphere. We were doing this for enough cases that Rick Anthony, I think Rick Anthony was the one who encouraged you to write this, or remember, I think I know he approached you and he approached me and they said, oh, this is really good, it's good to be a new era for synoptic meteorology. But we were actually focused on the use of these models for this kind of synoptic analysis and start unraveling the cause and effect aspects. All right, I'd love to go through post study too, but I thought I would at least compare. This only slide on here. This was the top. This is number 2 for DC. We're gonna have to update these slides. It didn't get updated on this system. It was updated on yours, but because we did the last slide on the previous slide too. So you got Press Day 1, Press Day 2, total snowfall record for Baltimore for this storm here. What was really interesting in comparison, this storm, the President's Day Storm 1 and 2, was the very heavy snow occurred with rapid cyclogenesis here. Almost all the snow of this record amount for Baltimore, it's like in the mid-20s, occurred before cyclogenesis actually commenced. When cyclogenesis commenced, we had a period of sleet and it was over at that point. Major amplifying trough, moisture feed from the Atlantic, near constant trough amplitude, moisture feed from the top. This is like an atmospheric river, all right? So the rivers just don't happen in the Pacific. This moisture flux was all the way down towards the equator. It's really a remarkable case. Not forecast even 6 hours in advance. By 2003, we forecasted this storm 3 days in advance. And the conference attendees changed plans to get back home in time for the event. I even had people in the private sector come up to me and say, hey, what are you going to do, Lou? And I said, I'm going home early. But I was going to go home early anyway because I wasn't going to miss this. So what's also interesting in terms of doing the work, it took years to collect, plot, and analyze the data. Years. Rich Grum wrote this, he pulled all this data together for President A2 and wrote a summary review in 2 weeks. So it was a pretty good review, I thought. Major effort by the research community, synoptic mesoscale studies. We had Mozart versus Uccellini, low level versus upper level, and we met in the middle. And then here, I don't know, I don't see the research that's been done on.
It's a gold mine waiting to be tapped, but with the ERA 5, it's on my radar.
Okay, so what I learned, first of all, everything was on the table on unraveling the mysteries. of the upper and lower limb dynamics, some of the balance constraints, unbalanced flow. I mean, it was really a remarkable time. And I know Lance will tell you about the cyclone workshops in which, Dick Reed and I went toe to toe, and Jack and I went toe to toe on the QE2. I mean, but it was not personal. It was like, everybody was rolling up their sleeves and trying to unravel this. Synoptic meteorology is not dead. I don't think it's dead today either. It drove the research community and the operational communities to work together. And the need to improve the operational models was recognized by the research community in a big way. So the other thing, I think this is the major message. I was told prior to this over and over again that studying snowstorms is a synoptic scale problem. And I believe strongly now that snowstorms and mesoscale events cloaked in synoptic scale law. And it amazes me how long, you get these 7, 6, 5, 4-day forecasts that show you snow's coming out during that pre-storm. I mean, by the time the storm hits, you're just worn out. And it's over in 12 hours, I mean, what is this?
Or it goes 100 kilometers.
Oh, it goes, yeah, that's even worse. So the time rate of change related to developments, cyclogenesis from minutes to hours should inform us of the balance and imbalance assumptions being made to understand what's really going on. The Russ Snyder paper, the 1987 storm in the Midwest, where high amplitude gravity waves passed through the cyclone during the cyclone's rapid development phase. Great case. And actually in Chicago, when the wave passed through the developing low, went over Chicago, the pressure was lower at the base of that gravity wave than when the storm went over Chicago. So what's going on there? Okay, what's the gravity wave? What's rapid development? So the last thing here, there's just, I feel very strongly about this, there's just as much joy in learning about these storms develop as there is in experiencing them. Okay? You already know that. You got Lance sitting here teaching you every day. So thank you very much.
Questions for Louis?
In that 7-layer model, how accurate was the forecast of at least the shortwave trough upstream in comparison to like the cyclone? You know the cyclone didn't really develop out in the model, but was the trough at least captured?
12 hours before, not 36. So, from and that's because by 0Z on the 19th, the trough had already amplified over the Ohio Valley, and it became more of an effective issue. So the trough really was not captured well at all. I would say 24, 36 hours in advance. And the PE model, which went out a little bit further in time, didn't have much trough in there either.
Do you have an idea of what kind of return interval what would the return interval be for that kind of forecast bust in the LFM if, say, we continue to run it? How many storms do you think would just not be captured even 6 hours in advance every winter if we had not done all of these improvements to our models?
Well, you mean like now?
Yeah.
Yeah. Now, what happened in the 80s and 90s into the 2000s, people like Fred Sanders and then Rich Grum, especially Rich, after Fred did it for a while, initiated, he sort of kept a scorecard on that. Found that getting where the models failed was in the rapid development phase of storms. You couldn't trust the models beyond 36 hours. And he basically said he had a statement in there about, inexplicably could not capture the rapid cyclogenesis. And then when we not only did the global, because global models really didn't go into operations until the mid-80s, and then we started the higher resolution of metaphysics. By the early 90s, Rich Grum was finding not only were we getting rapid cyclogenesis, again, not to the full depth, but that we were now more successful with the 3-day forecast, and that the false alarm rate even went down significantly for the global models and then regional models as well.
And then 93 happened, the storm of the century as it eventually became, was. We actually were predicting that storm about 5 to 4 days in advance, and it held up, thank God, on top of which we're standing here today. So, I was on the national news with that one before the storm hit. So the thing is, that was happening, and there was a sense that we had cracked the nut about that, the return rate of a failed storm was pretty low, right? And then 2003 happened, and, Steve Trackman's famous surprise. We actually had the storm, but we missed the west, it was off by 100 miles. And we're still seeing that today, even in the ensembles. There was a storm about 2 years ago off the East Coast that the ensembles were bringing in, and then it seemed to stabilize along the coast and had us in snow. And the storm went 100 miles further west of the ensemble mean that was used. And we wound up with rain in DC and sleet and that kind of stuff, mixed precip on the rest of Maryland. So, right, because people expect us to be making right on forecast all the time. So there's still a level of predictability with this that is a really important part of the problem. And I'd say that one of the biggest challenges that we face as operational meteorologists is that the expectation is that we're going to get it every time. And the predictability issue with this is such that we know we can't get it every time, but our return rate of that happening to us is actually growing in time. But it's something that still worries us.
So given the understanding of synoptic meteorology, for some comes the understanding of what causes hypergenesis and the role the PV anomalies plays in that, as well as the understanding that models weren't very good at even short-term forecasts. Do you think it would have been possible to expect this scenario to occur despite what the models were showing at that time?
Well, let's put it this way. This happened on a Sunday night, so I can't tell you, when we left work on Friday, I didn't see another map until Wednesday the next week. We didn't have access, so with respect to this storm, I couldn't tell you exactly what was going on. It didn't form an opinion about what was going on. I like to think that if we had seen that upper level trough at 0Z, there were some meteorologists that were emphatic that we still had to pay attention to this. Gordon Barnes, had a reputation for being a little, sometimes over the top with his long-range forecast, but he was on CBS, and he actually stuck with the snow. Got on 11:30 and said, this thing is going to be, bad news for us tomorrow morning. Some people were watching this and thinking, hey, we're not out of the woods yet. With respect to the potential vorticity, that's really a diagnostic measure of what's possible upstream. That's just, I've seen deepening troughs not generate those kind of storms. So you got to sort of have that right thermal field, that S-shaped thermal pattern, and as it turns out, low static stability, get the response that we got. I think part of the rapid spin up at the low levels was related to the decreased static stability. So it's all of the above. They all have to come together, which is why these storms are a rare event in general. And this is one of the conclusions Paul Kosin and I came to when we did the whole book on the storms, and we went back 50 years and came up with 35 cases that met the criteria. That's a relatively rare event. That's like equivalent to F5 tornadoes before this last 10 years used to get one a year. It's a relatively rare event. So I think all the ingredients have to come in here at play.
Which is why if you miss one, it's just so rare.
Yeah, then you're waiting, for the next one, and you can see, like, even in the one, I call it the apology storm, where they had New York hit, and it didn't, the gradient was right up and down Manhattan Island. It was really remarkable. And it was kind of interesting because the governor wasn't too happy with that, and neither was Christie down in New Jersey. But the emergency manager, Esposito, who runs the Emergency Management Center in Brooklyn, said that we had to plan for the worst and hope for the best. And he says, oh, by the way, last time I was in Queens was part of New York City, because Queens had 18 to 20 inches of snow in it. So I was like, you get into that kind of, demarcation zone, what can happen. You know that
you gotta have a strong stomach for this. That's just take that, I know you're laughing, but it's true. You gotta have a strong stomach. Yeah.
Do you remember if the New York and Philadelphia offices took as big of a hit as the Washington office?
Philadelphia had
Was there any
about-
effort to try to coordinate the forecast
No.
like we do now, or
No.
everybody was kind of on their own?
Everyone's on their own. The forecast offices, if you read, there's a book written, Allen's book about the Weather Service, came out in the early 2000s, basically described the culture of the offices, that every office was an island. And so the collaboration was not there. And as the head of NSEP, and I say this in forecast offices, I said it today, I had, as the head of NSEP, I had more interactions at times with foreign governments than I had with other components of the Weather Service. So that was one of the things that I really wanted to focus on in this job, is to make sure that we're fully collaborating, because we're more powerful when we do that.
In Philadelphia, New York, did they get it wrong too?
In Philadelphia, it was, everybody was taken down there, yeah, it was, satellite snow and looking at the southern edge of the satellite plumes and the low level part as the area that it was just sort of coming. So when this first high level clouds moved off to the east, the inclination was the show's over.
I was in high school in New Jersey at the time. I think I remember I was hoping for a few inches.
Much
And
more
I
than-
woke up to 16 or 18.
Yep. It's great to be on that side of
Just
the line.
north of me.
So, on one of these storms, my son lives in Burlington, New York, his family, and so that's just north of New York City, and he was complaining that he only got, for one of these storms, he only got, I think it was in January 2016 storm, he only got 8 to 10 inches of snow, and I says, hey, just go about 15 miles north, zero, talk about a sharp edge. It was incredible. So that's what I mean about the mesoscale aspects of these storms, rapid synoptic scale law, that people say, hey, we're gonna have a big storm and it's snowing hard on Long Island. You think, it's snowing everywhere, and it's not, or if it's raining on Long Island, you think it's raining everywhere. And 20 miles to the north, or, up in Connecticut, or just north of New York City, they get heavy snow, which you find about on the news and Friday for the rest of the night. So the thing is, this has been a signal that's there, and to fully appreciate it, you have to get the mesoscale aspects of this, as Dan did for the front. What?
Think about snow bands, so this is.
Yeah, so Dave Novak, he should come up here.
That's all we argue about, where's the band gonna set up, So,
After seeing such a presentation, you really, personally, I really appreciate how much the science has advanced since then. But now we know that there's a storm. We could see the storm 3-4 days before versus 12 hours before. But where do we stand relative to communicating the actual hazard of the storm? We all know that there is predictability issues still now on the mesoscale aspect, but are we matching our advancement in predictability with efficient communication, and where do we stand?
Okay,
Where is
so
doing that?
if you're asking me if we're matching that, the answer is no. Are we making progress in that area? The answer is yes. So let me just say that getting the changes we're working with now in terms of going beyond the forecast and warnings to actually connect with decision makers like emergency management folks, public safety officials, water resource managers, is the task at hand. Okay, so so communicating the hazards is one aspect of the challenges we're facing, and to have a full understanding of the impact of that. But there's many other challenges, and I just mentioned one, which I think is a critical one, and it was just written about by Rebecca Morris, paper Advance. There are changing risk preferences that you're actually messaging to. So let me give you an example, and we sort of discovering this the hard way as physical scientists, that when it comes to human factors, we really don't know much, okay? It's a whole new world for us. But if you're going to do a sort of a tick-tock of forecasted 8, 6, 4, 3, 2, 1 days in advance, and you're mapping out the increasing likelihood of something happening, whether it's a severe weather outbreak, which we do, right? A big snowstorm, flood-producing rains, heat waves 10 days in advance now, where we're talking about the potential for these. We follow the MJO and give forecasts for the hurricane, like the Atlantic's gonna light up next week, okay, which it does as it comes into the right phase. Your users have a risk preference, which is a wait and see, and confirm it with others. Other forecasts, their friends, their support, their groups, whatever, right? That's a risk preference. That's at one level. We know that 10 minutes before a tornado hits, that you're in a different space in terms of your risk preference. Where's the shelter? Okay. What happens in between that you're messaging now an increasing probability? Are you just wearing people out by the time you get to the point the morning of? A certain degree of that. So but yet it's now more important than ever that people act. You got to act before the storms if you're going to mitigate the impact. I'm absolutely amazed that states, governors, they declare states of emergency the day before a storm. In January 2016, they actually declared states of emergency in Virginia, D.C. areas, Point South, Maryland, and when the storm was forming, there wasn't one flake of snow associated with the storm at that moment that states of emergency were being declared upstream. That's an incredible leap of faith. Okay? To make those are real decisions that affect people's lives. So somehow, and it was important that they do that people had to understand that for 3 or 4 days, they better be ready to shelter in place, because they ain't going anywhere. You're gonna get 2 to 3 feet of snow. You're not going anywhere, right? So that is an important, I think, advancement, but can we do that better? By all means. Do we have, I talk to students now, there are universities doing these combined majors of meteorology and emergency management. That's what your new building is all about, right? Millersville is doing that. Emergency management communities are hiring those students because they need to know, somebody inside, not to try to duplicate our forecast, but to understand the messages that's coming so they can translate it into their action plan, okay? So that's happening, and I'm actually pretty proud of the fact that we're kind of leading the way on this with this Weather Ready Nation, but we're just on the front end of this, and there's a lot more that needs to be done.
All right, let's thank Louis. Okay, so you're gonna have to be here all the time. Yeah. Okay. First I want to show what don't help our bill. We're just looking at a big picture perspective here. All right, let's see. All I have to
Just say, don't show this message again, and no. There you go.
Thank you.
And enable editing. F5.
All right. Time myself. All right. So the large-scale flow pattern was characterized in that winter by distinct multi-week weather regimes, which has never really been understood or really examined. The major teleconnection diseases that we all pay attention to, PNA, NAO, and AO, are all negative. Magnitude oscillation transition from warm to cold phases during January and February, sort of like what we're going through right now without any action. And the oceanic Nino index was near zero during January and February and transitioned to weekly positive in there. So if we look at, say, for the month of January, the 300 millibar geopotential height field during January, you can see the nice wave, sort of wave number 2 with an appendage type pattern with the ridge off the west coast, moderate trough in the east. That's going to spill a lot of cold air down the northern plains. We've seen that movie before. And the 300 millibar geopotential height anomaly with that all across the top up into here, up in Greenland, in that area. And this is always a guaranteed recipe when you see that signal for cold somewhere in North America. And you can see the anomalous trough all the way up to Hawaii, all the way to, especially concentrated over the north central states, east and north of the Rockies. During February, the pattern elongated. It's almost kind of a wave number 4 pattern now, but the trough deepens out here and deepens into eastern North America. And now you have this different aspect with a deep trough on the New England eastward across the Atlantic with an anomalously strong Atlantic jet, anomalously weak Pacific jet with this big ridge sitting out here below normal heights down here. That's the easterly anomaly. So the jet was flowing up across the very high latitude in that area. So that's quite the transition. And this pattern just produced cold. And by the way, in the January pattern, I was in Boston that month, and there was over 10 inches of rain. So in February, low heights in through here, but note that with a deep trough out in here, this is March, this is right after the storm. So Louis mentioned we went to M+ in Washington, heavy melting of the snow, but why did that happen? You have a jet entrance region up here, look at this anomalously polar shifted and anomalously strong jet across the Atlantic. So a huge transition occurred in there. And if you look at the 850 millibar temperature, you can see during the month of January, the negative anomaly of the 500 millibar height is sitting core over the CONUS. And look at the 850 millibar temperatures that go with that. You're -5, -6, -7 degrees C in here. But note the strong gradient as you got towards the east coast. In Canada, was above normal. So it was cold almost everywhere except over the eastern part of the Northeast. Then you go into February, and look at now what happens. You've got this elongated northwesterly flow to trough off the east coast, strong anomaly there, and then the 850 responds to that in there with a big negative signal. That's what Louis was talking about for 3 weeks of cold at that time. So that was quite the transition. And then you go into the 21st, the day after the storm, into the mid-March, and you've got that big, remarkable ridge that forms out in there. You hate to see ridges like that in the winter. I'm really annoyed with the ridge we're dealing with. But it's the boss in there. And at 850 millibars, look at the core of the warm anomaly. So there are these big, multi-week regimes with abrupt transitions. Nobody has looked at that, to my knowledge, or understood what's the source of those regimes. Why 3 weeks, 3 or 4 weeks? How do you get into the regime? What breaks it down? These are all very interesting research questions of the subseasonal time scale. Now the MJO. So that's January 1st and through here. So you're in the warm phase. So and then you see this little loop here in phase 7. Where did we see that before? Last week in that discussion in there. Then it goes into 8, which is still not good. And then it goes, when you get into the blue is March, and the green is the cold. So it goes into the, but not very high amplitude, but it gets into 2 and the 3 and the 4 in here, which are cold phases of the MJO for us. And then it amplifies again, it stays in the warm phase, then goes right across the origin and back, and right at the very end of March it gets cold again. So that's the MJO pattern. But what happens when you have the stalling here? We saw it hypothesized with the recent case of the huge cyclone and that heavy precipitation over northern Australia that impacted the MJO and caused it to stall for a couple of weeks in one position. So, yeah, just looking at what phase, almost everybody looks just what the phase of the MJO says, and then goes and looks at the map. It's in phase 7, forecast this. That's the brainless forecast, but that doesn't have no understanding behind that. Why do you get rapid movement sometimes, loop to loop at other times? what's going on physically when that happens. We don't really know, not very few people are looking at that. And then the summarize of those are the indice values, which would favor on average during February, cold, you see the pattern. But no, the gospel is the PNA positive is cold in the eastern part of the US. Well, that's a pretty negative PNA. So you see, if you can't live by teleconnection index alone, that's statistics based. You need to think about the dynamics that's going on at the same time. The point that Kerry Emanuel made yesterday about statistics and understanding. And North Atlantic oscillation, though, was supposed to favor cold, so there's a battle going on in there. Okay. Now, just the next part. Let's see what we want to get out of this.
No, it's just, as you were showing that, I just brought it up, in 1979, in January, and it's January 13th through 14th, I think, go back to your meeting.
Oops, I took it down.
That was the Chicago blizzard that took down 21 inches of snow. It was one of the, at the time, it was the largest Chicago snowstorm in its history. And that was what was on the news, and I was thinking, when are we going to get into winter, right? And it was the next month. So that was the 13th and 14th of January that year.
So there's these regime change and regime persistence and transition are really important things to understand. But it falls between the cracks. The climate scientists are we're not really sure that that's relevant to us. The weather scientists say, well, we're not really sure that that's relevant to us. And try writing a proposal to do that. You're going to get killed by both sides. I wrote years ago a proposal to look at these kinds of problems. I got back reviews. The climate scientists said, this is all interesting, but it's not really climate. The weather scientists said, this is all really interesting, but it's not really weather. So you can't get funded in that kind of thing. So, but this is where the science is. All right, let's see.
I think the Chicago blizzard wasn't that good.
All right, now, let's introduce the ERA 5. With thanks to Marshall Failer and Tomer Berg and others, we now have ERA 5 books, which are really interesting when you start looking at what's going on. So I just see I made a couple of notes to myself. Grab that. Yeah, thanks. Yep, perfect. Okay. Standard on the compass. So let's look first at the compass, the 250. So this is hourly. No, this is not hourly. Sorry. Can't read this. Add that to my long list of known defects. Let's see. Standard 1, the 500 millibar. Just think that's coming up now. All right. First, we'll look at it 6 hours. One of the things you'll notice, go away. One of the things you'll notice here is the Vorticities contour. This is on the 3rd of February. So this is the month of February. And you can see the confluent flow of the continuous systems that come and impact the northeastern part of the 7th. That's the 7th. It's the 8th in there. That's a series of stuff coming down. Ridge on the west coast, which is what you get when you have a cold regime in the eastern part of the United States. In there. Now we're up to the 10th of February, the 11th of February. You see, one after another, these are sliding down and bringing all this really bitter cold air into the northeastern part of the United States. But now meteorological mischief making is in progress. On the 11th, out here, troughing off on the west coast. The blue, by the way, is the vertical motion at 500 millibars in here. And you can see the trough holds up, continuing to build the ridge. We're up to the 12th of February, 13th in there. And nice ridge. Don't go too far east, it'll ruin everything. In there. But the trough keeps rebuilding back to the west in the eastern Pacific. and now we're up to the 15th of February. Now things are gonna get very interesting out and through here. You get this elongated trough, with northeast to south, northwest to southeast orientation, so it's negatively tilted. But there are multiple vorticity centers. We'll look at this a little more carefully in a minute. But notice there's the southern stream system in here, but now there's all this action going on in the north. This is 0Z on the 17th. So the southern system comes in, but there's the northern system out here, and they didn't phase. The southern one gets out ahead of the northern one. So there's an issue. Phase or not to phase, that is the question in there. And the leading one has the biggest vertical motion. Note the northern one, which is critical to phase two, that Louis talked about in through here, has very concentrated asset match. And the southern one has this elongated, sprawled out stuff. The southern trough has access to the moisture. This one just has access at the moment to cold air. So note what it does. It gets behind this first one, there's all the strong asset with phase one in here. And look at that, there's hardly any asset indicated at 500 millibars at that time. But that's a rock and sock and vorticity maximum if you ever want to see one in there. And now it's amplifying, and then look at this is now at 6Z, go back. And that's what the coastal front on the coast. Watch the growth of vertical motion. Boom, bam, bomb. And bomb. Okay. And you can see the cyclonic evolution of the curvature.
Where's Boston when
There are a lot of times you've been in the rain, I've been in the snow. So this goes on endlessly. Sends me text in the middle of the night, you're gonna get gypped. And I'll send them an email wishing you 2 inches of rain, something like that. All right, so that, and then it moves eastward, away, so it couldn't come up the coast in this pattern, and you can just see what happens. All of a sudden, look at the flow pattern goes zonal, and there's the trough now in the west, and it's all over. Boo and hiss, and that was the end of winter. You can take a look at that a little bit more closely. If we look at the standard, if we look at the eastern conus. So Marshall Failer made this, but if we go to the relative vorticity, you will see these are hourly. Starts at the 0Z on the 17th. So these are hourly. The vertical motion's in blue in the winds. So the trough will enter stage left in through here in the southern stream. Down here, note the northern system's coming in, but there's all the action in the southern system in through here. And here's the northern trough, southern trough, and this is hourly. I mean, this is just phenomenal in there. So this is that little low that was out ahead, died on the west side of the Appalachians. This was the stuff that drove associated with coastal front. This is 13Z on the 18th in there. But here is what's going to cause the trouble. But again, yeah, you know, you look at that, you look at the vertical motion, your eyes all go. It's almost like looking at the satellite image that Louis was showing, and it goes offshore, and if you're not thinking and paying attention, the fat lady is sun, and it's too bad, and you're out of luck in here. But now watch what that does. We're up to 20Z on the 18th. That's a really compact vorticity maximum with a real concentrated area of vertical motion. But as it approaches, look how the trough is folding up and amplifying. And now look at the rapid, did something stupid. Now look at the rapid growth in vertical motion. And that's the stuff on the coast. Rapid growth in vertical motion here, boom, and it takes over. And this then, we need to rescale the vertical motion. We just went, you scared this to blue in the face, but you can't see what the individual values of maximum ascent are. So we'll get this right eventually on the scaling. But note the nice comet-shaped pattern of the vorticity, the trough, and the opposite. It's like the yin and the yang. Yeah.
So one of the, if you go back to,
This is 12Z and the 19th. Yeah, go back one more. 11Z.
yeah, so So the idea here is if the wavelength,
Yeah, correct, short,
dramatic, so dramatic shortening, which is a go forward. And I don't know, these are the vertical motion fields?
Yeah,
Yeah.
blue.
And all I know is the wave, some indication of wave
Yeah.
dynamics going on here, which is exactly, so the cases of, when Steve Koch and I did the synoptic background state for the gravity wave cases that have been published up to 85, that a trough ridge shortening wavelength, and Mike Kaplan always used the divergence equation to show how the Laplacian term in the, what's the other term, it's Laplacian and the, I'll remember it on the way home tonight. But they're both the same, they usually offset each other, but they're of the same sign when you get this kind of shortening wavelength that flow towards the ridge. It also sets itself up for both terms, working towards a divergent flow regime, not offsetting each other.
A corresponding way to look at that would have a shortened to the half wavelength from the trough to the downstream bridge.
Jacobian.
From the point of view of the air parcel, it's going from the trough to the downstream bridge. It's going from a high vorticity region to a low vorticity region in a relatively short amount of time as the wavelength shortens downstream. So associated with that, going from the environment, there's going to be a lot of vigorous assay associated with that.
Whenever low level stuff's coming up, it's coming up like this and out.
Yep.
It just struck me how it's the same type of flow regime that will give you a gravity wave mode, as well as the rapid cyclogenesis.
Now, if we look at the water vapor transport, IVT, I mean, I've just been enthralled the last few days, ever since Marshall and Tomer started showing me stuff from the ERA5. It's like, why would we use any other analysis? This is the Catz-Fial level of analysis. There are still some issues. That's
I can clear out the disk space of CFSR and air interim
No,
now.
don't do that. We're talking petabytes, but watch the, how the water vapor transport develops separately as the upper level system, the second one we were just looking at deeper. See, we've got the main area outed through here, but no, look what happens in there. And then what does it do? It wraps right around. See that? That's just beautiful. We had no idea about this.
And that's what the Hibbett, when we did what was the predecessor to Viz 5D, that's what we saw on the, and you could actually follow the trajectory scheme.
Yeah, but think what this means for science. We can do calculations. It looks realistic. You can calculate stuff. What's from this grid point data. This changes everything. This is a real revolution to have the ERA file. I'm not trying to exaggerate. It's going to happen. So wrapped around, and, well, next point, look at service frontogenesis. Get back. There. All right, so where are we? We're at 22Z, we're at 0, this is 0 to the 18th into here. You can see the broad northeasterly flow. I mean, actually, the cold advection going on all the way down as far as Florida, offshore. And as we already mentioned, there's a big 1050 high up there, in there. And you can see coastal frontogenesis is starting, that's with the southern system along the coast of the Atlantic. And through here, now have the winds now become easterly and northeasterly onshore in there. And boom, tighten the gradient in the first phase of the storm. Where we,
What level is that?
this is 0 to the 19th.
Yeah, but what type of, this is.
Oh, surface.
This is surface.
Yeah. So it's 2D Patterson frontogenesis calculation in there. And look how the winds develop the inverted trough, and this is really a very, very strong coastal current in there. And it's so beautifully seen in this analysis. It's just stunning to me.
I was saying one of the Holy Grail problems was working with Louis was the limitations in temporal resolution of our data sets.
Yeah.
This was the Holy Grail that that barrier we never thought we could break, but here we see it has been broken.
So we did it with the last two papers, we had 15-minute data with again, we had somebody tell us that's all you could fit on the case. I wanted to go to minute data, and they told me to pound salt essentially, but the thing is that getting the temporal resolution of the data sets is what really allows you to get into whatever cause and effect on that you want to study.
And then you can see what I was talking about before, how the rotation is it holds up here as it moves off the coast as the circulation develops, pointed right back towards the coast. And the last piece of this to show is, let's go back to zeros again in 19. The heat fluxes, that's the precipitation view. So this is the sensible heat flux in watts per square meter every 100. So that's 200, and that's 100 in there. And then the latent heat flux down into here, 500. And this was in my 1981 paper in there. But the key thing to note is these strong heat fluxes, but if you look where the low is, it's down here. So one of the points I made in the paper was that the heat flux is sensible latent heat maximized ahead of the low, as Louis made before, not behind it, where it's all described in traditional textbooks in the cold outflow behind it. Why was it so important to do that? Because you've got a big and all that cold air pouring out over the warmer one.
Can you go 12 or 24 hours back from this one?
Oh, sure.
So you go to,
This is 12Z on the 18th.
yeah, so that type of heat flux is going on for a good 24 hours.
Yeah, that's helpful.
Yeah, the destabilization of the boundary layer is
Yeah.
incredible.
Yeah. So, I mean, to see these, and the numbers are pretty close to what I guessed by a crude analysis that I did 40 years ago. And it's like, so, it's really something to see that, I was not totally out to lunch in my 1981 paper, only partially out to lunch. But we were getting numbers in the right ballpark and the importance of the heat flux. So, this, I mean, and the thing, the LFM, as Louis pointed out, it only used mandatory levels. It didn't use significant levels. I stood up at AMS meetings and got shouted down by the NCM brass. I said, NMC brass, I said, you need to use the significant level sounding data. You're getting it wrong. You weren't getting the boundary layer profile right because you're only using mandatory. And I got the standard response at that time was, well, if you knew more about numerical weather prediction, you'd know that the model will spin itself up and get you the answer you need. And I made the comment at one meeting after that speech, I said, well, what if the answer was the wrong answer? So I could make trouble, just like Louis could make trouble.
I remember those meetings. Yeah, so the other thing was, first of all, the challenge of running a model operationally, I don't underestimate the engineering aspects of that. And couple that with having to meet a real-time schedule, which one of the drivers to what could you actually do in the window that you had for data access, data quality control, whatever data quality control effort you were putting into it. And then actually doing the analysis, initializing the model. And you find that takes up so much time of the whole 12-hour window that we had, that was one of the, it's like how much processing can we actually do?
I understood that. My argument was, why weren't they in the parallel mode in research? Why weren't they, trying to advance the state of
Nice, but after 10 to 20 years of just getting that engineering issue worked out, that was a major task. But still, when we did show them this case, that you were not going to get away with just the standard level data sets, it was pretty clear that the new leadership and NMC behind Obama really made a difference.
All right, just a couple of the last things. Tomerberg, I want to show this, made a hourly surface from the ERA5. So he's got the hourly observations plotted, 0Z, the 18th, and you can see as things go through here, you'll see the coastal front develop. we're at 12Z, and it's 18's in the 18th here. See, that some of the winds are shifting easterly here, you got northerly having from here, and, okay, no, right in through here, Tucson River is north with heavy snow, raining at Salisbury. The coastal front sitting right up here, right up in Chesapeake Bay, for example, in there, look at that. Strong northerly flow here, or northeast, east-northeast in through here, as the low comes up in there. And this is all, these odds are plotted on the European Center's one-hourly analysis. You can see the strong gradient out and through here. Wouldn't surprise me if there's a sting jet out there. We talked about it class just the other day. I know the asymmetric distribution of the sea level pressure gradient on the west side in there. So you see so many of these things, and Tumor also had the hourly precipitation. Why isn't that right?
Just back up a little bit, I think in the earlier times.
Yeah, you're after the storm ended, so you want to step back about a couple hours.
It's not, it's like frozen.
It's moving back.
Oh, there it goes. All right, but the only point about Baltimore, this is 11Z on the 19th.
Mr. Nefsky, I'll zoom in a little bit. It's kind of hard to see.
There's a point, where is it? Here, this is at 14Z, 0.35. Next hour, 0.30. Well, what's that? 0.65 with wind. So, and there's problems measuring snow and wind. So that's the 4, 5, 6 inches an hour snowfall period in there. Wow. That gets you going. And whoops, there's the track. Tummer's figured out, by the way, that we can throw away Hodges. Not literally, but all these algorithms that track cyclones. With the ERA5, you have hourly data, so just doing simple interpolation. Simplified, it's going to change everything again. And being able to track features, vorticity maxima, surface cyclones. This is going to facilitate a Lagrangian interpretation of weather systems. Again, I cannot overemphasize what a game changer having this kind of analysis is going to be. And look how, here's the main phase 2, there's the initial cyclone that tried in there, but note how the coastal front development allowed the storm to get pulled northward along the coast so that it could be intercepted by the track of the disturbance coming from the west at 500 miles. Then they phase locked. And all this is the period when it caught up with a very rapid deepening that occurred. So this is just fantastic in there. Minimum sea level pressure. And you can see from the ERA5 analysis, it gets down to about 87.5 in there. But here's between about just before 12Z, starting about, this is about 9Z and through here, the bottom falls out. Remember, this is diurnal rise time and through here too. So the bottom falls out during that period. And then once it phase locks, it stops deepening and oscillates around. Once that upper level disturbance catches up with the surface.
There's a question for you, Lance. If you redid your 1981 paper, every figure you did with these analyses, how different would your figures look and would your results sound?
Most of the results would still be very similar, but the figures would look orders of magnitude better. Some things I would need a student to do the orders of magnitude better, because you all know that my technical skills are not.
There's an opportunity here, in a sense, to revisit these old papers.
That's right.
The landmark synoptic papers that change how we think with these current data sets and say, what would our insights have looked like with those data sets? When there's your work, Dick Reed's work, Fred Sanders, all of those events, some of those case studies could be revisited.
Oh, gosh, yes. And going farther, we could quantify so much we couldn't do that before.
So one of the things that Kissel was doing, the first re-analysis was initializing model runs like for the November 1950 storm, which was the storm we used for the first numerical prediction, and found that if we had had data that a storm was predictable 5, 6, 7 days in advance. So those kind of studies, in terms of these types of low pressure systems that were like, monumental storms that caught people unaware or just weren't predictable enough for anybody to take action, were they actually predictable or not? Right? And it turns out that most of these, even in the December 47 case, without the data, further back to the original, 1.5 days of predictability. But if you had analysis like this that actually went back, you could actually show that a lot of these storms were. Did this go back to 1950?
It will eventually. We're at the moment 1979.
1979.
So it just made it squeaked it under the wire.
Most reanalysis projects like this stop at the 1950. Because that's when the radio saw network was cool.
But the plans to go back to 1950, there were some big storms.
Yeah. We can redo the whole President's Day, the whole sequence.
Somebody else could redo it.
Well, there's a comparison with the 2003, that's one that's always been on my agenda, that never got to it, but, no, so, my time is almost up in all this, I'll be ready for the funny farm in another couple of years. But, all you young people in the audience, this is a spectacular, opportunity, that it's gonna take a while, but it's gonna take a while to dawn on the field what the opportunity is, in doing this, to really advance the state of the science. So, you might say, meteorology, I would say this is the rebirth of synoptic dynamic meteorology by having this kind of analysis available. And I taught far too long, it's time to turn it over to Kevin and Andrew. Their stuff is up here, I think. Yeah, I'll let you take it. I'll just screw it up.
And I'm looking at that satellite picture, it looks like.
Yeah,
it's-
Kevin, just go back down to the bottom where you were.
Oh, yeah.
That's that link.
Mississippi.
Yeah. February 1st, it starts to be a weather season. And with early springs, there'll be rowing boats down in Mississippi and Ohio River in a couple of days.
All right, I'll try to be brief with this. I'm just going to connect the storm and that shortwave trough that's been talked about in terms of the phase 2 of the system, in terms of a dynamic tropopause and a coherent tropopause disturbance that was associated with the shortwave trough. So, I guess back when all the analyses were carried out on the storm in the 80s, the tropopause analyses weren't available. So, looking at the features I was mentioning here weren't really possible. So, the feature of interest is a coherent tropopause disturbance, which is just a tropopause-based 4C, and which is like a material feature characterized by a local minimum of potential temperature on the dynamic tropopause. And you may have heard of tropopause polar vortices or TPVs, and they're just a subset of these TPVs, but they just originate from high latitudes. And to show an example, this is from Matt Kyle's work with Dan and Lance. We have this map of dynamic tropopause theta on the left in the shading, and on the right, dynamic tropopause pressure. And we have this CTV/TPV here over Canada. We can see a localized minimum of theta on the CT and maximum of pressure, indicative of a locally depressed tropopause. And that kind of depressed tropopause structure is what we saw with that shortwave trough feature in the President's Day storm. And the dynamical importance of CTVs and TPVs were shown back in Hopkins et al. 85 in terms of cyclogenesis, where if you have a localized depression of the tropopause where you have an upper level cyclonic PV anomaly, whether it be a shortwave trough, CTV, or TPV, moving over a low level baryclinic zone, you can have a cyclonic circulation associated with this disturbance acting at the low levels, helping to induce warm reduction downstream, which will give rise to a positive thermal anomaly or cyclonic PV anomaly / surface cyclone downstream as well. And that surface cyclone is going to have its own circulation that can impact the upper levels and impact the structure of the upper level PV field via positive PV advection upstream. And over time, these systems can become phase locked together and mutually amplify one another. and kind of show the system of interest for the storm. We're going to look at a dynamic tropopause plot on the left here, which shows theta in the color fill, wind speed in black contours, and wind by large. And the right is no kind of maps we've been looking at, upper level wind speed, thickness, and sea level pressure in the water. So we're going to start a couple days before the cyclone's development by focusing on this region of lower tropopause and low theta air off the coast of North America here. This is a region of cold air that was originally from the higher latitudes that came on down. And we're going to see that over time, as this area of lower tropopause air moves eastward in the downstream flank of this ridge, it's going to start to ball up. And we can see by 18Z and the 17th a distinct minimum of theta on the DP, which is classified here as CPD, or coherent tropopause disturbance. And as this feature moves on the downstream side of this ridge, it will start to kind of ball up as it perhaps gains some increased curvature vorticity, and we start to see this CPD become more well-defined, more axially symmetric, and more circular. And we can see to the south of the CPD is a localized jet streak where you have that increased temperature gradient on the tropopause, which increases the localized wind speeds there. And as Andrew will show, and has been shown by Louis, Dan, and others, there is subsidence occurring within this jet streak adjacent to the CPD, which help give rise to the tropopause fold that occurs. And we can already see a downstream response to the CPD over the Ohio Valley, where we have this very weak surface cyclone, and we can see the surface frontal trough off the east coast that will be CPD approaches the President's Day storm. It helps it to rapidly intensify, because by this time on the 19th, the stratospheric air associated with the CPD was reaching downwards towards the boundary layer, and may have helped to increase vorticity in the lower tropopause and vortex stretching. And another thing to note about these CPDs is that the more circular they become, the more likely they can have a deeper velocity penetration depth, which can more effectively help a system like the President's Day storm to amplify. And then the CPD and the cyclone will become kind of vertically stacked and then move in tandem with one another as the system kind of gradually weakens and oscillates in intensity. And I kind of show that CPD from the perspective of the literature in the 80s. These are kind of similar plots Louis showed earlier, where we have the shortwave trough feature shown by this 312 Kelvin isotopic analysis with the jet streak. Here we can see the total wind field and localized polar jet to the south of the structure, and the tropopause fold occurring beneath the upper level jet streak. And so once that feature moved towards the east coast, we have all this dry air shown in this water vapor imagery associated with that jet streak and that coherent tropopause disturbance, almost becoming vertically stacked with the surface cyclone located just downstream, where we had the ozone maximum located just upstream of the cyclone. So that's all I really have, and if there's any questions, happy to take them.
The visualization of this, because I think you'd really be excited about it. That the film I had from Hibbert, that Hibbert and I did. If I could?
Yeah,
Yeah,
that'd be great.
But I have to load up, get back to, should I try to break your system?
It's Windows, it's already broken.
What do I do here? Yes?
No.
No.
Yeah, I mean, right.
You have to lead me through it every time. Just to show you the difference. That's the,
Oh.
oh, wait a minute. So I hit this one first. Yeah, there it is. I found it.
Oh, wow.
All right, so pretty primitive, right? But these are the folks that were involved in this. We wound up publishing this in only So here's the potential vorticity we were just talking about. And this is gonna be looking from south to north through the, so one of the, so there's the white tornado I was telling you about. There's the bottom one. So this is why McIntyre stuck on, he's only gonna spend an hour with me. Stuck the whole
You
day.
see the phase locking. Most
There's
of
the
the
phase locking, yeah.
upper level features, just like Kevin was showing from a dynamic topos
Right.
perspective.
And here's the trajectory.
So what this, your visualization showed is topos folds were three-dimensional vertical features.
Right.
I think it wasn't appreciated until the visualization that was the case.
And you can see, remember I said the thing about the trajectory, see it's moving with,
Yeah.
and then this one moves through, and these move through the, and in the longer version of this film, we look at it from east to west, and it goes, once it goes through on the slope, it's like the slantwise convection. Now here's the low, and you get the phase locking, it's like this, and then it goes horizontal vertical, so you start with this, and it goes, starts doing that.
Lou, another comment was, you mentioned a couple of times, trajectories are moving with the feature. That's a sign of a vortex, not a wave. That were a wave-like feature, the trajectories be moving through it. And that's a very different dynamical perspective than what Norm Phillips was looking at in terms of cyclogenesis from amplifying baroclinic waves. So it was a new perspective, and it took time to sink in.
And it took a lot of time just to create that. But that part of the film is like, at least 1 week's worth of work before it got there. And then going through each one of those cycles, Hibbert would say, go out for lunch. When you come back, it'll be done. And I said, just eat lunch. He says, we'll go out for a beer. So, it was really a tremendous amount of work doing that. Now, one of the other things that I noticed when you were doing your analysis, when you were showing your analysis, when you're looking through from south to north, that's the only area that's happening in the whole model domain. It isn't like these things are all over the place. You got lucky, and you were basically showing that these, have to line up just right. And
You see that on tropopause maps.
Right.
These are localized features, and they're not just, they're not randomly spaced.
And when one of the only proposal I got rejected ever was by using the toms and this together, we showed that this was where, that Danielson was right? That this was an exchange between the stratosphere and the troposphere. And that it generally only happens where the tropopause faults are happening. And we wanted more cases to show that versus this magic dispersion or diffusion that would happen for whatever kind of exchange that the upper atmosphere people use it. So I sent it to the upper atmospheric component of NASA, and they got blown out, 3-0 reject. I'm sure they sent it to the folks who were all into that this type of thing only happens, that there aren't these major gaps. And I was really shocked actually, because I thought Danielson, with the nuclear particle dispersion, he was showing that could, the upper level, the atomic weapons were tested in the upper atmosphere first, because we all knew there was no interaction between the stratosphere and the troposphere. So why worry about it, right? And then strontium-90 started showing up in milk.
Atomic chickens came home to roost.
So it's really, so what you're showing is, it is really a unique aspect of this entire flow regime. And for it to come together with that kind of storm, everything has to be honest with that. So, anyway, that's what I want to show you. After we saw this, and I said, like I said, when I showed this at the Palmain conference, and I had a long, when you look at it from east to west, you see that red, well, it's like the slantwise convection that people were starting to talk about. It was really amazing, amazing to see. So.
We should be doing these kind of things like on a regular basis. Or the ERA5 data, why not?
Not on the train, not on the train.
Lance,
Sorry.
my battery's on fumes, so I'm gonna probably need to cut off soon. Well, as long as my battery holds up.
All right, so the goal of
what I want to show is just some sort of newer analysis with respect to the Sawyer-Eliason type circulations that were shown in that Uccellini et al. 1985 paper, using the CFSR analysis to sort of dig into what you can use with some of the more reanalysis products. Can you still reproduce some of the same circulation features that are shown in that particular paper? And just a sort of background on the Sawyer-Eliason circulation equation, it's a way that you can diagnose some of the transverse circulations associated with active fronts. You get it through using the geostrophic momentum approximation, the thermodynamic equation, and your momentum equation, retaining some ageostrophic infections, temperature, and a long front wind. And through that, you can then begin to diagnose some of these mesoscale frontal circulations that play a huge role, at least in terms of the application of that feature that Kevin just showed on those previous images that he had. And so that's the equation in all its glory here in the yellow right here. And what's important is that when you focus on this equation, it's a second order differential equation. What you're really interested in is the stream function psi, because it's from this stream function psi that you can diagnose the vertical component of the circulation versus via the sort of a long cross section gradient of psi, and you can also return the horizontal or horizontal branches of that circulation by taking a vertical gradient of that stream function psi. And the way that we're going to define this is our y-axis is going to be pointing in the across front direction, so imagine a cross section cut perpendicular to any sort of areas of baroclinicity, and then your x-axis is going to point in the long front direction with colder air to the left of that. So in this equation too, you can also the circulation itself, one way to sort of conceptualize what this looks like is if you just imagine yourself standing on the beach here in Mobile Bay, the jet stream's directly above you, and then this circulation is almost like a ring on a finger in terms of the way that in this sort of conceptual model that it's circulating the jet structure here. This is sort of what you have in sort of the sense of a jet exit region type circulation where it's thermally indirect in that particular type of structure. So the stream function psi basically returns to you what sort of the sense of that circulation is. And so then when you dig even further into the equation, if we look at these coefficients that modify basically these gradients of psi, the first one basically is a representation of the static stability of your frontal zone. You can imagine that your second one is a measure of the across-front baroclinicity, so the strength of that frontal zone, another sort of measure of that. And then finally, you have a measure of the geostrophic absolute vorticity in the vicinity of the frontal zone. And when you consider all of these three things together, these are some of the sort of the three leading characteristics of fronts when you think about some of the changes in wind direction in the vicinity of these structures, the strong baroclinicity, and the strong localized static stability. So these are all sort of modulators on the structure of the circulation once you look at it. And this paper by Hakem et al. In 2001 does this from sort of an idealized and conceptual standpoint to try and diagnose what are the impacts of these various knobs on the strength of the circulation once you dig into it. You can see strong absolute vorticity translates to a more upright circulation. It's confined in the horizontal here. You have a baroclinic circulation, it's more of sort of a slantwise type circulation that's aligned in the sort of the direction of the baroclinicity here. These solid lines represent your potential temperature, I believe, if I'm correct. And then static stability modulates the vertical extent of that circulation. So stronger static stability, you can imagine that circulation being squashed in the vertical compared to situations where you have maybe a lower measure of that. So that just gives you a sense of, in a very sort of quick sense of how these different knobs can control the structure of the circulation sort of from a mathematical standpoint. And then finally, what does the whole entire show here are those geostrophic and diabatic forcing terms. We won't focus too much on the diabatic forcing term here for the sake of time. This was located upstream of that developing TPD or CTD that Kevin was looking at, so diabatic processes weren't particularly important. So shown here is the cross-section that was calculated in that Uccellini et al. Paper from 1985, drawn from A to A prime. You can see it cutting through or immediately upstream of that developing upper level trough. This is a map of your Montgomery stream function on the 312 Kelvin isentropic surface. You can see a nice attack of winds right here in the sort of upstream side of that trough, northwesterly flow, and we're cutting this cross section right through the entrance region of that geostrophic wind maximum. And then so if we look at the sort of a comparison of what you get from the CFSR versus what was calculated within that particular paper with respect to these cross sections. Shown here is what's in the Uccellini et al. Paper, and this is going to be wind speed out of the, or sort of perpendicular to the cross section, so wind coming out of the board here. This is going to be sort of the northernmost portion of the cross section. This is going to be the southernmost part. And then you have to do a little bit of mental gymnastics here because the way I wrote this actually outputs the cross section in the opposite direction. So this is A prime, so this is the southern side of the cross section. This is your more northern side. You can see the colder air here located to the north here near the boundary layer. And then also notice that this cross section is cut off around 750 millibars by comparison, where this goes from 1,000 up to 100. So you can see a pretty good correspondence between this wind speed maxima directed out of the cross section here.
Andrew?
Yeah.
Yours is coming out, ours is going in.
Yeah, yours is going in, I'm sorry. So this one's coming out, this one, that one's going in. And so you've got this strong jet maxima here that's associated with that northwesterly flow. And then also if you compare that to the wind speed or the geostrophic wind in the plane of the cross section, you have an area of confluence that's diagnosed here within the Uccellini et al. Paper, and then within the CFSR you have a much stronger region of confluence than diagnosed within that particular analysis, keeping in mind that there's different analysis schemes being used between these two metrics as well in terms of how things are interpolated into the cross section. But what's also, you take the vertical gradient here of your geostrophic wind in the cross section. You have a thermal wind that's directed pointed towards the northern side of the cross section. So in the context of what you're viewing here, you're looking at a situation where you're characterized by geostrophic cold air convection within the plane of the cross section too. So in the context of sort of Mel Shapiro's conceptual model, you'll imagine that circulation being shifted so that you have subsidence located directly beneath the jet core itself. And so this is what you get when you actually solve the equation itself. This is the solution from the Uccellini et al. Paper, and then the solution what you get within the CFSR cross-section that I calculated there. The blue contours are your subsidence, and then the circulation in the plane of the cross-section here is going to be directed in a clockwise type manner here, so you have some subsidence occurring on the area of the strong developing orbital front, which is conducive to the extraction of that high PV air. That's shown really well in that particular paper, as well as from Kevin's analysis as well. And just quickly for the sake of time too, you can break down these circulations into both the horizontal shear term and the confluence term within this sort of Liouville equation. This is the horizontal shear term here, so you can see a shift of that thermally direct circulation towards the more equatorward side of the cross section, so that you have that subsidence located directly beneath the jet core. And then also for the confluence term, you have a degree of a thermally direct circulation in the vicinity of that area where you had that strong confluent flow when we looked at the geostrophic wind within the plane of the cross section. So there's some notable differences here between the two analyses here, but the bulk in terms of the result of diagnosing that subsidence in the vicinity of the orbital front is consistent across these. So that's what you get when you put everything back together here. And for the sake of time, I think I'll leave that here in terms of sort of a quick and just a quick analysis of sort of a comparison of what you get using the CFSR. But I think going back, especially with that ERA5 data and trying to draw the solution for these equations with that higher resolution data set and comparing it to what you have in light of some of the discussion we have, I think would be really interesting in that context. But yeah, any questions on?
I'll make a comment. I think it's reassuring that we basically got the answer right. And that was, you remember more, but that was an objective analysis that Ralph Peterson had devised based on radius-on data. And I think it's really amazing to see that, at least we're on the right track.
Yeah, that was where we used horizontal and cross-section analysis in concert, so you could get the gradients in the right place for the right reasons. That whole transfer of the gradient information from the vertical profile to a horizontal Yeah, one of the things that struck me, go back to the equation where you were talking about the static stability curve, and you showed where it filled the hole. Yeah, right there.
Yeah.
So that was a real wake-up call, I think, when I was studying this stuff, plus Dan kind of blew me away when he came in and showed me how to make this work. But that it fills the domain space, so that your horizontal, return aspects actually, can influence the depth of the atmosphere that you're studying. So the trouble pause is really important for focusing the horizontal branch up there on the surfaces. And it turns out, I always felt, after going through this, that the static stability curve, people didn't understand how it modulated the nature of these transverse circulation patterns to fill the entire space. And the reason I was included, sort of looking for that, John Young was trying to explain this to me at the University of Wisconsin about why are you getting the world, why is the indirect circulation that you're studying focusing the low levels in the low levels and in the return branching levels, and how does it relate to static stability? So when I see this coming out, Ray Dan's work was like, yeah, that's what really helped return the whole circulation, fill the entire troposphere.
All right.
I'd like to introduce our two undergraduate students, Chelsea Snide and Brennan Sutter.
I just want to preface this with there will be a lot of overlap with Lance. Kind of coached a lot of our maps that we were planning on looking at. So.
Always be useful from a different perspective.
Okay, so I wanted to start off talking about this map, which is the mean sea level pressure and then thickness and precipitation type. So if we back up a little bit, so we're starting at the beginning of February 18th. And so at this point, this anticyclonic circulation is going to be moving over the northeast, and that's going to increase the easterly winds, pushing that cold air up against the Appalachians. And so we're going to see this this nice big cold air damming signature going basically down the entirety of the Appalachians. And then as we move forward in time, a shortwave trough kind of slides around the bottom of the cold air damming and starts to build this inverted trough around the coast of Alabama, or I'm sorry, off the coast of Georgia and South Carolina. And so that's where we'll see our surface low start to form. And by early in the morning on the 19th, we see that at this point, this precipitation field looks a lot like a normal extratropical cyclone, where we have this localized strong precipitation with what will be our cold front, and then broad, lighter precipitation overrunning the warm front.
So to set up the picture for the low level forcing, this is the 850 data EMAP, and this is right now at 18Z on the 18th, and as Brendan was talking about, you can still kind of see that cold damming signature where we have the colder temperatures kind of hugging the Appalachian. But what's more interesting is this baroclinic area, kind of the Carolinas and Georgia. But as we step through time, we see this small shortwave disturbance is helping to bring in more southeasterly and southerly flow throughout the coastal region in Florida and along Florida as well.
Can you stop to just quickly on one? And at 65. Yeah. 65 knot wind there in South Carolina.
Yes.
And then notice the 35 of the coast into 65, and that's where the low-level divergence max along signal sort of I was glad to see that, to see that it actually captured, this analysis actually captured the magnitude of that.
Yeah, no, definitely. What I wanted to point out on this map with the low-level forcing was that with the predominantly southeasterly and southerly winds, we have a lot of warmer convection north and into the Carolinas, where Louis and had that big maximum divergence over this region. But also we have east-southeasterly winds onshore into the Carolinas, so the southerly and the easterly winds are going to really help push the temperature gradient together in this region and really cause a strong area of baroclinicity.
Okay, so moving on to integrated vapor transport. So if we back up a little bit on the 18th, this is right when this this initial first shortwave is starting to move down into Georgia, and we still have the trough upstream working its way eastward. And so as the southerly component increases because of that shortwave rounding the bottom of the Appalachians, we start to get more vapor transport coming from both the Gulf of Mexico and east of Florida up into what will be that warm sector. And so that is helping to increase the instability in the lower levels, and it's also giving fuel for that heavy precipitation that we'll see a little bit later in the storm. If you look at another map that Lance looked at, okay, so first I wanted to start with the 850 frontogenesis. And so moving back again, this is 12Z on the 18th. And so you can see this shortwave trough starting to come in, and then, see, I can't really see the other shortwave on this map here. So you move forward a little bit, you see that warm air advection starting to increase with that southerly wind, and then you can start to see the wind shift come in, and this will eventually start turning into our warm front that we see forming right before that rapid cyclogenesis. And if we go down to the surface, we can see more of that cold front starting to form, and that really strong chronogenesis along that coastal front, which is supporting that initial surface low that will eventually turn into the bone.
So what me and Ren were kind of interested in looking at was the storm from a QG perspective. So we were looking at Q vectors, and this is all from the CFSR, and we are starting at 0Z on February the 18th. And this is kind of in the initial development of the storm. So as you can see, we have some weak Q vector convergence off the shore and into the Carolinas, as well as the secondary local maximum downstream of what was that shortwave trough at 500 and in the upper levels. So we see these two systems, and as we step forward through time, so this is 12Z and 18, we see that these two disturbances are going to start to merge together, which is when we saw our rapid cyclogenesis. So we have our Q vector convergence both off the shore and associated with the short wave trough starting to merge together, and as well as grow stronger. And by 0Z on the 19th, we really start seeing these two systems superimpose on each other and growing stronger, as well as indicated by the larger values of Q vector convergence. And by the 12th and the 19th, which is when we really see the storm coming, we see this really significant maximum right off the coast of Virginia and into the northeast as well. Oh, this is 700, sorry.
Yeah, so just to reiterate what we saw with the 500 millibar vorticity. So this is once again at 12Z on the 18th. And we can see this vertical motion near that coastal front, which doesn't have any strong vorticity advection. If I didn't have this blue, I would probably think that most of the vertical motion would be here. Probably would have never guessed that that would have that signature down there. And like we talked about before, this is that warm front starting to form and a little bit of the cold front forming. And then as we move forward into the 19th, you see these maxima in vertical motion come together into one strong maximum vertical motion. And, yeah.
So lastly, we are moving up to 300, looking at the jet, and kind of how we already talked about. The jet stream wasn't as significant in the initial development and from what me and Fred discussed, but it really helped the rapid cyclogenesis in the later period. So that's stage 2. Okay, so this is the 21Z on the 18th, and we kind of have pretty zonal flow with this trough propagating eastward, which is going to help bring in at the rapid cyclogenesis phase. But currently, with this jet stream here and what Louis' diagrams really demonstrated well with the AGS roving flow, we aren't really getting too much forcing from the jet stream at this time, as our aquatorward entrance region of our jet is pretty displaced westward and a little bit southward. So our best forcing is really not in the area of interest. But as we move forward and this low starts to develop from the low level forcing, we start getting into this region of the aquatorward entrance region of the jet, really amplifying the upper level divergence. And as we move forward, and as we see this surface low getting stronger, it actually moves to the other side of the jet. So now we're in our forward exit region, which is going to be amplified with the upper level divergence, as well as being downstream from this trough feature. So we have that combined upper level forcing at 300, but earlier it wasn't too significant at the lower level.
Comment, jet crossing is common with these strong cyclogenesis events. And I think Lance made the point earlier that what helped make it possible was the elongated coastal front, the vorticity, corridor that had formed already for the flow to move along. So it's just, and mechanisms for jet crossing aren't really well understood. So you identified a very good problem.
Yeah, Brendan and I were discussing about it earlier, that it's kind of interesting that we saw that, because usually, at least I haven't seen it kind of happen in storms that we've forecast before, so we were kind of confused.
So one cautionary comment. So for the earlier jet being up at 250 millimeters, this is part of the problem, the challenge that one has with pressure
these horizontal slices, you don't see them. Or that's why when we were doing our analysis, we were doing it in pressure coordinates and pressure coordinates, and that's how we decided on the 312 systems. So that southern jet might not be visible at 250 millibars, but I guarantee you that between 500 and 300, it would be very visible. And the upper level jet would not be as visible as we show here. So I'm not sure what you mean by the jet crossing. I can
The
see
cyclone crosses the jet from the anticyclonic shear side to the cyclonic shear side.
They're two different jets, right? So you're on the anticyclonic shear side of the subtropical jet, but as the polar jet comes in, and it's not really shown well at 250 because it's maximized about 300 millibars or even lower in this case. It is on the cyclonic side of that, but if you just plot one pressure surface on it, you see this crossover. So that was one of the frustrating aspects. I gotta tell you, we spent days, months, years trying to understand this until we finally got the analysis done in the two different coordinate systems to see that we were really dealing with two separate jet systems, subtropical and then polar. So I'm not sure what it's meant by crossover, other than that representation on one pressure surface gives you that.
Probably time for it, not enough time for it now, and I'm thinking of the subtropical jet as a feature that was being crossed, and then the polar front jet's on its way to ignite the cyclogenesis. If I'm saying it right.
Love to sketch it out on the map.
But the process has been noted in the literature. The question is, I don't know if the cases have been looked at from a three-dimensional perspective to identify separate jet features.
And I do. Thank you. Analysis at 300 to 400 millibars, would you get the same interpretation? Right. That's, I think maybe that's one way to find it. Show you might not see the full magnitude of the subtropical jet, but the polar jet would be clear in the whole sequence. And, you know, you would see, I think, a different perspective.
Thank you.
Quick 5-second question for Tyler and Alex.